So tonight we have another wonderful lecture, public lecture, by Professor Badri Krishnan from Einstein Institute for Gravitational Physics. Black hole idea is one of the striking ideas in modern science, the history of modern science, which traces back to John Michell. Professor Badri Krishnan, I think, will take us through all this history to LIGO. So please enjoy. It is, I guess that will be a very, very interesting lecture for black holes. Black holes is a part of human culture. So it will be very nice to listen to this public lecture. Please let us welcome, thanks the speaker once again.
Thank you. So this is going to be by far not a comprehensive history of black holes. I mean, I'm not going to do that here. And if I repeat the talk, I'm sure I will add more and more things. But it's a completely biased, with no attempts at completeness kind of thing on the things that influence me in the work that I've done for black holes. So I make no apologies for that. So for example, even though some things I really like is black hole, so entropy calculations and black hole thermodynamics. But I think this is the golden age for, in fact, the classical theory of black holes, not so much the quantum stuff. In the sense that, sure, there will be advances in quantum gravity and they will discover new things about black hole entropy and other things. But the key thing is going to be, in my view, the observational results from gravitational waves. And these are essentially dealing completely with classical physics. So the important part, in my view, for the next, in the near future, is simply the classical structure of black holes. So that's the thing I want to focus on. I'm not saying the others are not important, but that's the thing that I'm focusing on here. So I'm going to start again with this picture. And so yesterday, Scott gave a very moving picture of the way that he felt when he saw these pictures here. So I have much more of a mixed view on this topic. So for me, the first thing I saw was closer, in fact, to this thing here. I didn't really see that until much later. And also, the first time I saw this, I had complete belief that this was not a real signal. And we're in the process of trying to figure that out. And also, I had really no, and this might sound strange, since I've been working in LIGO since 2002, I wasn't emotionally attached to gravitational waves, to be honest. So it's not that the gravitational wave detection, I had no doubt that they exist. I had no doubt that the signal would look more or less like this. And this was not. For me, the key thing was finding black holes in our universe and looking exactly like the numerical relativity simulations that I'd seen many, many times before that. So for me, the black hole aspect was the key thing, and that is somehow comparable to what Scott felt by looking at this thing. For me, it was the thing that produced this signal. So anyway, be that as it may, this leads us then to, for example, results like this. So this is a simulation of these two black holes with some star field superposed in the back. And this is a full numerical simulation solving Einstein's equations. So you see the two black holes orbiting each other, getting closer and closer.
What's the sound?
This is meant to be the sound that the speakers here are not as good as Scott's. So I'll turn off the sound for the next one. And this is then the second one. This is the neutron star binary event. Previous one was simulation by the SXS collaboration. This is from AEI. Again, you see these neutron stars orbiting, the waves being emitted. This is zooming in on the neutron stars now. These are balls of fluids, so they now merge, form this object after the merger. And this will, and you can see here the waveform as it goes on. This is the post-merger phase already. And at some point, this will collapse and form then a black hole. So this is one scenario for what might have happened. Of course, the late part of the waveform we don't really see, so it's only a guess about what that thing could be. And apart from these, I mean, there's also other observations of black holes. So Luciano will talk about the Event Horizon telescope results, I believe, in the next days. There's, of course, the beautiful observations of stars at the center of the Milky Way. There's X-ray binaries, there's quasars, so all kinds of things, right? So from the situation about, I guess, 30, 40 years ago, when astronomers didn't really believe black holes existed, so now being invoked to explain all kinds of phenomena that they see, so we've come a long way. So now let me sort of move to the part of, what are black holes? So often people say, and I've also said it many times in talks I've given, so gravity is so strong that even light cannot escape. This is not quite true, as we'll talk about, but this part of gravity being so strong, but still, so I'll sort of go through in what sense this is true. So for this, let's first recall the term black hole was first used by John Wheeler in 1965, I believe. And though I don't actually know if he was the one who coined the term. There was, I believe, somebody in the audience who suggested the name, and they never figured out who it was. So there's somebody close enough to John Wheeler, I guess. But before that, so back in 1724, there was a guy called John Michell, which I know many of you may not be aware of him, but he was actually quite an accomplished scientist. So he was a fellow of the Royal Society back in 1760. He was professor of geology at Cambridge in 1762. And if somebody's called him also father of modern seismology. I don't know if that is true, but I've seen it applied to him. So a very distinguished person. But then I guess his real passion was astronomy, so he left it all and then went to Yorkshire as a clergyman in 1763 and started doing astronomy and all kinds of things. And even made a large telescope in 1780, which was later bought by Herschel. And then his paper on black holes, which I'll briefly describe in the next slide. So this was written in 1783, and this was communicated to Cavendish, who actually read the thing. I mean, actually, I didn't know they actually physically read the paper at the society meeting in 2 sessions, so in December 1783 and January of 1784. And essentially what Michell did was he considered that light particles, they fall the same way as material objects. And this is, of course, not true because light follows, as you know, null geodesics, and material particles follow time-lag geodesics. So it's not quite true, but this is what he was considering in this work. And I could not find, in fact, any image of Michell. So I mean, this is sort of a strange thing about how less known he is given his accomplishments. So in modern terminology, this is not the way at all that his paper is written. So I mean, I took the time to go through it. It's really very, it's in the Newtonian way of drawing parabolas and finding areas on the curves and these geometrical things. So in our terminology, what he was doing was he was looking at a star of mass m and a radius r, and he was considering particles falling on a star from far away. So these could be material particles, could be light. And then he derived, I don't know if this was known before him, but he certainly derived this equation in that work, which is that the velocity of a particle that falls on a star from far, far away is going to be 2gm upon r. And then he converted the mass into a density and a radius, so assume a uniform density star, so then the mass is 4 by 3 pi r cubed, and then you put that in, you cancel the r, you get the velocity square given by the rho times r square. Okay? And then he said, well, somehow at the time it wasn't common to assume an object of much higher density, at least for stars. There was no reason to do so. So he said, let's think of an object which rho is like our solar density, and let's keep on increasing r. And at some point, if you keep on increasing r, keeping rho fixed, v is going to increase. At some point, v will reach the speed of light. And from what was known about speed of light for him, it was again a strange way in the paper that is written about how he got the speed of light and put the numbers in. But essentially, he figured out that a star with the solar density, but 500 times larger, so then for such a star, you will get v equal to c. So imagine then our star expanded 500 times, and at that point, suddenly all light from that star will shut off, and that is then the object that he's considering. And if you set v to c, then you get the radius of the star to be this thing 2gm upon c square. If you set g and c to 1, this is precisely the Schwarzschild radius for black hole. So it's a coincidence, I suppose, but it's an interesting thing to keep in mind. And this was in 1780 or 17 whatever the date that was. And roughly at the same time, somebody much more famous, so Laplace, I mean, all of you know his contributions to celestial mechanics and mathematics and statistics, in fact. So I won't repeat them here, so I mean, he doesn't need any introduction. So his paper, which was very similar, and it seems there was no contact between him and Michell, so it seems to have been completely independent.
It is controversy.
It is controversy? Okay. Okay, so this...
people say
okay. So anyway, so he was trying to, again, prove the things that Michell was claiming independently. And then, and again, keep in mind, this was the time of the French Revolution, right? So this is towards the end of that. And so I won't go through the thing that he calculated, but it was a very similar thing. And in the end, he also went for not a small, dense object, but the giant sun. So in fact, his final outcome was a star which was 250 times the size of the star and 4 times its density. I don't know exactly why this precise number, these combinations, but anyway. So in this case, an even bigger star. Okay. And again, even in this case, of course, it's clear that this would also become such a dark object, and even light cannot escape from it. And of course, I mean, all of this in Newtonian gravity, so the speed of light is not privileged in any way. And the light that is sort of falling on the star is changing its speed, right? So there's nothing, this is not what we would think of as light at the moment. But anyway, so after this, nothing seems to have happened for a long time, until we reach 1916. So exactly just a short time after Einstein found his field equations. And then, of course, Schwarzschild again, maybe, I don't know if you're aware, but he's actually very well known for work in optics and electrodynamics and astronomy. So for example, he was the first person to write down the full action for electric and magnetic fields along a whirl line of a charge. And then he was posted on the Russian front, and he died in 1916, so from a disease that he contracted during the war. But this was enough time for him to figure out the first exact solutions to Einstein equations in spherical symmetry. So he just took the Einstein equations, imposed spherical symmetry, and found the general solution to that. And his conditions were not ideal working conditions, you might say. Okay. So this is something that he wrote to Einstein just at the end of 1915, so shortly, a few months before he died. As you see, the war treated me kindly enough, in spite of the heavy gunfire, to allow me to get away from it all and take this walk in the land of your ideas. So, don't complain about working conditions. That's the message here. But anyway, the point was that he did the work, and in our terminology, he derived this metric here. And so m is the mass of the central object. There's no other parameter. And you see that this metric, this is geometric unit. So if you want g and c, it's just 2gm upon c square r as usual. And if you see that if I set r equal to 2m, then this diverges, so something is wrong at that surface. And also, of course, if r is 0, then that is also divergent. So it was understood that r equal to 0 is a real divergence, but nobody really knew what to make of the thing at r equal to 2m. And in fact, this is somehow strange, but no one actually understood this properly for many, many years after that. And there were various people who sort of looked at spherically symmetric solutions in different coordinates. So Pine-Levé, Gullstrand, Eddington, and so on. But somehow they didn't quite realize that they had redrawn the Schwarzschild solution. What they found was the same as what Schwarzschild had. So they hadn't really quite made this connection. It's only in 1932 that Lemaitre found this different system and made the connection to what Schwarzschild was doing. So it's actually a long time, right? 16 years for this feature to be not even understood, but not fully understood, but at least this aspect of it to be understood. And in fact, it took even longer. So 1960, imagine, right? So we're talking about decades after the Schwarzschild solution is written, with huge amounts of confusion in between and all kinds of frozen stars and what have you. So this picture, this is the modern picture, which I'll describe in detail just now. But this was obtained only in 1960. So it's like almost 45 years after the Schwarzschild solution has been found. So these were the dark ages of relativity, I guess, of 1920 to 1960, more or less. And in this case, so let me go through this here. So this is now what is called a Penrose diagram, Penrose-Carter diagram. This is not the form that Kruskal-Zacharias wrote in, but doesn't matter. This is the form that I want to describe it in. And this is a visualization of the largest possible extension of the Schwarzschild spacetime, the same metric that Schwarzschild derived. And what this is the following. So each point on this diagram is a sphere. Okay? So somewhere here will be observers who live. So as you go, this is the black hole region. This is the external region. And observers far away from the black hole will be somewhere here. In this diagram, light rays go at 45 degrees. So there'll be light rays going here and light rays going, in this direction inward. So that's this N and the L directions here. And this is what is known as null infinity. So this means that once if you follow light rays, go with them as far as possible, then you end up on this surface. If you follow spatially outward directions, then you'll end up somewhere here. Okay? So the point is that light always goes at 45 degrees. So nothing is stopping light from falling inside this region. So you can shoot light rays and you can fall in. But once you cross this surface and you try to come back out, you can never reach this region again. This is r equal to 0, that's a singularity. So, and also these are curves of constant radius. So if you set a particle at the same radius, it'll follow curves like this. If you want to find slices of constant time, you'll get slices like this. Okay? But the point is that once somebody enters this region, and they assume they can't go faster than light, so they can only go within the light cone, so they are doomed to reach the singularity in whatever amount of time they have left. So this is then the black hole region. So once you reach here, then you cannot come back out. And again, in this picture, light is always at the same velocity. So this is not the same as a Michell Laplace black hole, but this is really fully relativistic. And this surface r equal to m is called the event horizon. So once you fall in, then you cannot come out. And if you live long enough, then you will reach the singularity in a finite amount of time. So this solution also has these other regions. So you can also, in principle, be connected from here. You can't reach here causally from this region, but this is sort of the other asymptotically flat universe. And this is what is called the white hole. In a realistic situation of collapse, these regions are really not relevant. So what is relevant is the exterior region and the black hole region here. Okay, so don't worry too much about this, but just mathematically speaking, you can extend the solution and get also these regions here. Okay, so this is now the modern picture for what a Schwarzschild black hole is. So now comes a Kerr metric, and I have to now here include not just Kerr, but also Ted Newman. And I don't know if people realize, but Newman could have been the first person to have derived this metric, except he made a sign error in one of his calculations. And he had to be content with the Kerr-Newman metric, but I think that's still, given his other accomplishments in the field, I think that's okay. So this is the metric. I'll just write it down like this. It won't make any sense whatsoever to you. This is not as simple as I don't expect to understand any of this. I just it's much more complicated than the Schwarzschild metric. The funny thing is, if you calculate anything for the Kerr metric, things look complicated, but the end result is often very simple. So this is sort of a mystery that happens with this metric. And the importance of this is this quote by Chandrasekhar. So in my entire scientific life, over 45 years, the most shattering experience has been the realization that an exact solution of Einstein's equation of general relativity, discovered by the New Zealand mathematician Roy Kerr, provides the absolute exact representation of untold number of massive black holes that populate the universe. And this is completely true, of course. So it is remarkable that you have this exact solution found purely by mathematical procedure that works amazingly well over enormous length scales, right? I mean, you really have to be, a tiny black hole with huge quantum effects and so on that would actually show any deviations from this. And astrophysically speaking, if you have black holes for almost all of their existence, right? Think of any matter around the black hole. The effect of the matter on the black hole will be tiny. It'll be absolutely negligible in most cases, the vast, vast majority of cases. So it's completely true that this solution that was found by Kerr is in fact the perfect representation of all of these black holes from these enormous length scales. So unlike stars, which have a lot of parameters, right? And any object here like this glass has huge number of multiple moments and all these complications. But for a black hole, you just need 3 parameters. And for astrophysical black holes without any charge, you just need 2 parameters to describe it almost completely. There'll be small deviations and so on from matter fields around the black hole or some things orbiting the black hole, but really, to an excellent approximation, this is absolutely true. The only time that this is not true is when, for example, there might be other mergers, I guess, but really the important one where this is not true is when 2 black holes merge. So for the very short time, so compare the whole existence, right, billions of years, for this very short time when they are close to each other, they will be deformed due to each other's gravitational field, and they'll be very different from a Kerr black hole. But apart from that, this is an amazing fact.
For that case also do exist exact solutions?
Not an exact solution for the binary black hole. This is the simulations I presented. I'll come back to that. Yeah, that is true, but it won't represent. Right, so there are sort of special solutions indeed, so that is true. So there are special cases where you can write them, but the full merger process, the dynamical space-time, emission of gravitational waves, so that will not be described by any exact solution that we know of yet. Okay, so I was saying, so this is again, a huge amount of, this is seminal results in general relativity, which is that the Kerr metric is a unique stationary black hole solution with a regular horizon. If you include charge, the Kerr-Newman black hole, it has just 2 parameters if we ignore charge. And for all physical environment, almost all, the effects of surrounding matter, that's going to be very small because the amount of matter is going to be small compared to the black hole. And M upon R cube is a tidal force exerted by sort of matter near the black holes. That's going to be small. And the only time they deviate is really during a black hole merger. So it's an interesting question of how a black hole goes from this complicated merger distorted phase to this final equilibrium phase. And that's a sort of very interesting topic of research, both for numerical, astrophysical, mathematical reasons. And this is sort of the heart of black hole physics these days. So now let me go back to what is a black hole. So the question I asked before, is gravity always so strong near a black hole that even light cannot escape? Well, let's just look at that just with some numbers. So if a black hole of mass m has a radius r that we saw already earlier, so if our sun were a black hole, it would be 3 kilometers in radius, and its density would be more than nuclear density. But if I had a much bigger black hole, the density would be much smaller. So if I look at m upon r cube, and I put r proportional to m, the result is 1 upon m squared. Okay? So the black hole center of the galaxy has density about 1,000 gram per centimeter cube. If I have black holes bigger than that, so that's quite realistic, you could even reach density of water or even lesser density. So it does not always mean that black holes need to be very dense. Big black holes will be much less dense. In a different way you can think about this, look at the surface gravity. So on Earth, the surface gravity is 9.8 meters per second square. You can look at this in general. So surface of a black hole, the surface gravity goes like inverse of the mass. And once again, for larger black holes, you have much smaller surface gravity. And if you have stupendously large black holes, much bigger than actually exists in the universe, in principle, it could be so small that you fell into such a black hole, you really wouldn't even feel it. And yet one more way to look at this, look at tidal forces. So when you stand on the Earth, there's tidal stretching of you that happens because of the Earth's force. You get stretched a little bit. And the stretching is proportional to proportional to m upon r cube. Okay? And once again, that's inverse of the mass squared. So on the Earth's surface, if you just do the calculation, imagine someone who weighs about 100 kilos and is 2 meters tall, then the force that is stretching that person would be about 10 to the minus 4 newtons. On the sun, it's actually smaller. It's 10 to the minus 5 newtons. But if the Earth were a black hole, this would be enormous, would be 10 to the 22 newtons. So this is the spaghetti effect. So if you really are near astrophysical black hole, you'll be stretched and made into a strand of spaghetti. So you won't actually fall into the black hole. If the sun were a black hole, this would be 10 to the 11. And for the black hole in our galaxy, the force is just about a newton. So not that much at all. So again, if you fell into a big black hole, you wouldn't feel anything. So gravity is not really that strong for these big black holes. So let me look at this in a different kind of way, okay? So let me look at now properties of light near a black hole. So the first concept I want to introduce is what is called an expansion. So imagine a bundle of light rays. So each of these lines represents, with my great expertise in graphics with computers, these are light rays. And imagine a small infinitesimal area spanned by these light rays. And there'll be cases when the light rays expand, and that is a situation in which you have positive expansion and you have convergence, that's negative expansion. And you define this quantity called the expansion as the rate of change of the area divided by the area. So just remember this one little definition, okay, expansion. There's other optical effects. So there's expansion, this is called shear. So this is very much like the effect of a gravitational wave on a detector. So these are transformations that preserve the area but squeeze and stretch in perpendicular directions. Okay? So that's a shear, and there's a twist that is really a rotation of that little cross section. So these are the optical effects that happen with bundles of light rays. How is this relevant for black holes? So this is now, I'm going to come to a different sort of field of very important results in black hole physics. So if I have a round sphere in flats, imagine just a sphere, okay? So I don't really have, just imagine a ball. And imagine sort of light rays coming out from that sphere in all directions, in perpendicular directions. Okay? So of course, I could think of a very distorted sphere where this would not be true, but just think of a nice round sphere in normal space. The light rays that go outwards are expanding, right? That's again clear. So if you compute the expansion of these light rays, you'll get a positive number. And if you look at the light rays that go inwards, they'll be converging. Okay? So those light rays have negative expansion. Okay? Now the really amazing thing, which again perhaps is not emphasized really as much as I should in my view, inside a black hole, if you have these nice round surfaces, they are such that the outgoing light rays also have negative expansion. Okay? This is really hard to imagine actually. So it's a sphere like this, and you have light rays going outwards, but the little area spanned by these light rays is actually decreasing. And it really takes a while to sort of wrap your head around what this is. So this is what is called a trap surface. And this is, I think, the right view to think of why light is really trapped inside a black hole. You have the limit, you have what are called marginally trapped surfaces, those which have zero expansion. This is even harder to visualize, I think. So mathematically, I can write down all equations, I can really spend hours talking about them. But this is not so easy to visualize. They're very, very strange properties once you impose this condition. So imagine again a closed sphere, light coming outwards, but again going parallel to each other. So zero expansion, right? So that's a marginally trapped surface. So again, going back to this picture that we had before, each point is a sphere, I told you. So any point here, the light rays going outwards have positive expansion. The ones going in have negative expansion. For a sphere exactly on the horizon, the light rays going out have zero expansion. So this is a very, very special surface with very special properties. And the light rays going inside are converging, so they have negative expansion. And once you're in the black hole, everything is really converging. Okay? So in this special case, this event horizon coincides with these zero expansion spheres. So this is sort of a nice way to think about why is it that even light cannot escape from these black holes. I mean, the fact that somebody here cannot reach here, I mean, that's an important fact. But if you really want to see why is light trapped in a local sort of sense, this is the way to think about it. Okay? So now I want to talk about, in this context, again, somebody called Ray Chaudhary. So he passed away just recently, and sort of an interesting history with him. So he was from India, so he lived and worked in India all his life, and he joined sometime in the 1950s or late 40s or something, I believe. So an institute in Calcutta was in an association for the cultivation of science as a research fellow. Okay, finished his master's, didn't have a PhD at this point, and he joined this institute. And his topic was meant to be crystals, X-ray crystallography. Okay? And nobody in the institute knows anything about GR or doesn't even care about GR. Nobody really bothers about it. And somehow he never really wanted to work on X-ray crystallography. I mean, I'm nothing against X-ray crystallography, but that's not what he wanted to do. Okay? So then he left the institute for some time and then came back again. And then he wrote a paper in 1953, which he sent to Physical Review. And again, was a long process, and the paper accepted only in 1955. Okay, so might say it happens to many people. You send a paper, it takes a long time. But this paper was a seminal paper in this field. And none of his colleagues actually thought anything about it, and they didn't really care. They didn't really want him to do any of this work at all. They'd rather that he work on something else or just leave or just be done with them. Okay? And again, he doesn't have a PhD yet. He wants to submit his PhD thesis. And so he submitted his thesis in 1960. It's like 5 years after this happened, right? And then he's really not very happy at this point. You've got to keep that in mind. And somehow, John Wheeler was the external examiner on his thesis committee. Again, I don't know how this happened. I have no idea. Okay? But it is a fact. And then, of course, Wheeler realized, I mean, also it was known, this paper was published in 55, so people have already seen this. So people outside India, they know how important this paper is. And then because of Wheeler, he made sure that he not only passed his thesis and got his PhD, but with honors. And then he got a faculty position at an important college in Calcutta in 1961, just 1 year after that. Okay? So not a very typical career. And again, keep in mind, I mean, he has no way to learn GR at this point except purely by self-study. There's no professor there teaching him relativity. He's only doing all this entirely by himself, and everybody around him, doesn't care for anything that he's doing. But things worked out in the end for him. Yeah.
Someone must have supervised that piece, at least officially.
Not that I know of.
Okay.
So, I think there was, of course, an advisor, formally speaking. I don't really know the relationship. There must be a historical study of this. Well, so what did he do? So before, again, keep in mind, before this work, a lot of effort was spent in trying to derive exact solutions which satisfy certain conditions and to see if, really have singularities and, so all this exact solution problem. What you really want to know is to understand in generic spacetimes, is collapse and singularity, are they inevitable or not? So he is dealing with cosmology, okay? So Ray Chaudhary's purpose was cosmology and the Big Bang singularity. So the general question he was trying to answer was whether things like anisotropy or rotation or cosmological constant could possibly help us avoid the initial Big Bang singularity. So this was his goal, right? And this is what he's trying to show. And he's not trying to show this for some specific solutions, but he's trying to show this generically speaking for any space-time set in some very general conditions. So he derives this equation, again, for this expansion, the thing that I just mentioned. So he shows that if you imagine sort of a bunch of particles following time like geodesics, with all gravity, everything taken into account, that the expansion of these, in this case not null rays, but these time-like geodesics, again the same concept holds. You have these rays, and you want to look at the separation between and little area spanned by these whirlwind of these particles. Okay. So the rate of change of the expansion in a suitable coordinate system is given by this expression here. And the right-hand side has the expansion squared itself. It has the shear square. So the shear, remember, is this effect here that I told you about. So this you can represent as a complex number, and then you get the shear squared and the twist squared. And you get one extra term which has information about the space-time curvature. And if you then impose Einstein's equations, this is related to the stress, to the matter distribution. Okay? So what you see is that if you want sort of to have this focusing, so what does this tell you? If a lot of these rays meet at a particular point, that's convergence, right? So there you want theta to become large and negative. So the things that make theta negative are this term and this term. Rotation can oppose that effect in certain situations. And this term, if you impose any of the energy conditions, this term is also positive, so that also makes it more converging. So then the result that you get, and you can analyze in the detail, is that if theta is negative at some point, then it will generally become more and more negative. So now you got to think future and past, okay? If theta is, let me do this. If theta is negative, it converges to the future. If theta is positive, it'll converge to the past. That is the Big Bang singularity. That's a cosmology case. Okay? So these are the future and past trapped cases. So now this is, again, by itself, this is maybe not that, this doesn't tell me fundamental, right? Light rays can converge at a point. These are just caustics, right? So just the fact that all these rays meet at a point by itself does not tell you that the space-time is singular at that point. So the next step in this is something that sadly Ray Chaudhary could have gotten that with the right mathematical background, but he just didn't have that background. So this is then where the Hawking-Penrose singularity theorems come in. So using, again, this, everything after this point is based on the Ray Chaudhary equation. Okay? So this is Roger Penrose, that's Stephen Hawking. This must be in space. Okay, good. So, and you need one more key ingredient to describe the singularity theorems, which is these closed trap surfaces that I told you about. So it is not enough just to have these light rays converging, but you need to have the presence of these closed surfaces which are trapped. And what these people showed, starting with Roger Penrose, so this is sort of the deepest, one of the deepest ideas that I think is ever introduced in black hole physics, that due to Roger Penrose, the existence of these closed traps, the very definition of these surfaces. If they exist in a space-time, and with the energy conditions and so on, then it is inevitable that there must be singularity to the future. So this is then the question, in general, what happens in GR? Can you avoid singularities by doing some strange things to matter and so on? The answer is no in general. Okay, so the precise result is sort of harder to describe. Essentially, it is proof by contradiction. So if there are closed trap surfaces in a space-time, then geodesics are incomplete in the future. So something strange will happen at a certain point, and that is what is thought of as a singularity. So now let me go to binary black. These are now single black holes and general things about singularities. So let's now go to binary black holes. This is then getting closer to the present and to binary black holes. So already realized in the early 70s that, or even before that I guess, that binary collisions of black holes would be very important as gravity wave sources. So already in the 70s, people started sort of thinking about doing numerical simulations of black hole collisions. And there were several advances very important advances in how to sort of write Einstein's equation in a way that you can evolve things in time. How do you understand horizons in these situations, numerical methods for doing these calculations, and all kinds of things. But still, for a long, long time, nobody could get these damn black holes to merge. So you run the code crashes, numerically things are unstable, nothing just worked. But there were very interesting scientific results. So this is from 95 or something, I believe. This is what is called the binary black hole grand challenge. One of the main results of that was this event horizon for two black holes colliding. But still, before 2005, so that's when we get now very close to the present, so Franz Pretorius made the big breakthrough. So this is showing that numerically, you can actually start with two black holes far apart. In this case, they were not far apart, but still far enough apart, and evolve them, make them merge, and get the final black hole. So in this picture, what is shown are the tracks of these black holes. So there's the centers of these horizons. These are a different numerical resolutions. Just focus on the black curve. So this is something that goes here, and then it's the other way around, and then the black holes then merge. And this is the gravity wave signal that you get from this merge. This was again from Franz's paper. So this is a component of the curvature. So it's known as a particular part of the Weil tensor component here. And you can convert this to a waveform, NH plus and NH cross that you see in detectors. But you don't need to do that. This is the full waveform for this situation, starting from a very short in spiral, the merger, and then the ring down. So by itself, this waveform cannot be used. It's too short to be used in any analysis, of course. But just the fact that this could be done, I can't tell you how important that was. Okay? So for decades, people have been trying to get these black holes to merge, and they were using coordinate systems where the black holes, you were co-rotating with the black holes, so black holes are really not moving. So just let the black holes move. I mean, just this plot, I know many people really working in this thing. Just to see the black holes moving on these tracks and colliding, this was like the key thing that they needed to make the next really big advance. So just let the black holes move. So very short, and also keep in mind, Franz, so he was doing something really not in the mainstream of any of these simulations, right? He was doing things really all his own way. So for some time it wasn't clear exactly what he was doing that makes this work. But in the end, just like the black holes move, and then soon after that, groups at the Rochester Institute of Technology and Goddard, so So they also managed to get evolutions, and then the floodgates opened, right? And then once you can get these black holes to collide, then you have this huge parameter space. Well, not huge because there's not so many parameters, but still a very large parameter space that you can explore. You can start black holes much further away with different spins, and you let them merge, and then you see what happens. And most importantly for us, what this means is that we can use now these black holes to look at the data from gravitational wave detectors. So in fact, very soon after this, so this was roughly in 2005, 2006, with these other results. So by 2010, we already had the first models, or 2009, which went all the way from in-spiral merger to ring down, which were in fact good enough, and they're not, they're not super accurate, but they are good enough. And those were then improved, and those were used in the analysis that I showed in the LIGO results. And I would say that it's not that you needed the numerical simulations themselves to be in the detection paper for LIGO, but the models used by these simulations, so those were very, very important to understand the event. So numerical simulations were extremely important to understand the first binary black hole detections. So I'm going to stop here. So again, it's a very short and completely biased history of this field, so I make no pretense or no apologies for this. But we started from the 18th century and got to LIGO. Again, it's a long time before Schwarzschild discovery was understood. There was this golden era in the 60s and 70s. And then this amazing breakthrough happened in numerical simulations 15 years ago. And this is where we are now. So the golden era is yet to come for classical black holes. We have a lot of time for questions.
Wasn't Chaudhary equation so specialized to some really special conditions when there is no rotation, and we have some energy condition that I'm not sure.
Yeah, so I did mention the energy conditions. So that you can argue is general. I mean, that is going on the matter fields. So the important thing for the black hole case is that what you think about typically are, if you have this closed trap surface, and you think of light rays coming out from it, you look at the whole surface formed by the light rays. And then you can in fact show that for these light rays, the twist should vanish. Okay? So in fact, it is not specific at all. So except for the energy conditions, it's really true that you really need these negative terms here. That's all. So this was a key thing. I mean, this is not looking at specific conditions, specific symmetries, really a very, very generic setup.
Other question?
One comment. So the nerve I remember in 1998, it was 99, Bert Kalup.
Yeah, I was.
So this was a group in Germany. It was the first person, I think, to attempt to evolve two black holes actually orbiting around one another. And it did 1/4 in orbit, and the code crashed. That was considered a triumph, actually.
Yeah. That's
so
right.
It really was stunning. It was just 6 years later that Pretorius had this breakthrough.
Again, the field is full of people who were not doing things the mainstream way, right? So think of Michell, think of Schwarzschild in the World War in the trenches, think of Ray Chaudhary dealing with people who want to do X-ray crystallography,
What was the problem? Why did the codes crash?
The gauge conditions, effectively. It's not that they were so far from that. They could have gotten that earlier if enough people had tried enough things.
No other questions? Let us please